Our next speaker is a professor. I call him Professor Sri, but the right full name is Thambipillai Srikanthan. Okay, Professor Srikanthan has recently completed 6 full years as the head of the School of Computer Engineering, which has 1,800 students in NTU Singapore. He has been appointed last year as the executive director of the university level Cybersecurity Research Center. His research interests include design methodologies for high productivity embedded systems, architectural translations of compute-intensive algorithms, and many more. Please, Professor Sri.
Thank you very much for the conference organizers to give me the opportunity, and I'm truly privileged to be among the eminent speakers of today. Learned a lot. It was so difficult for me to plan as to a 15 minutes talk and what is that we are to convey. Partly my boss wants me to publicize the center. I am more interested in the research topics that are being investigated. So end of the day, I've decided to go for a hybrid. So I'm going to go through, unfortunately because of the pressure of time, I'll just go through the overview. Obviously, we can have discussions offline. So it'll be in this order. It'll be just a brief introduction to our cybersecurity research at NTU. It's one of the 2 main universities in Singapore, and you know Singapore is always very proactive, be it in its initiative towards smart nation, innovative solutions, and just to make sure that they're progressive in all aspects. So very, very fortunate to be part of that momentum over there. And then I will talk about a semantic-based security analysis. I'm just putting that into a context of 3-prong approach, and I'll just go through that reasonably quickly. So this is what we are. This is a college of engineering. We're predominantly a very large college of engineering with about more than 600 professors. We got School of Computer Science and Engineering and Electrical and Electronics, Nanyang Business Schools, Humanities, and Rajaratnam School of International Studies. They talk about international law and policies, and physical and mathematical sciences talks about cryptologies and crypto work, theoretical computer science. All these marked in red are essentially joining forces to embark on cybersecurity research at the university. And the center that we are putting together, though, it's essentially trying to partner with eminent international academic institutions, just to be able to make sure that we are current and able to complement each other. At the same time, we are also trying to attract industry participation to be able to give us useless problems so that we can try to be a little bit more relevant in the investigations we pursue here. And at the same time, we also have agencies, government agencies, that are also trying to bring us problems that are use-led. Essentially, for their operations, they need solutions. So we thought it'll be nice for us, instead of trying to be, instead of being abstract and in isolation, how do we work together and cross-ignite this ecosystem? At the moment, we are very fortunate about 3 spin-offs technologies in the pipeline for commercialization. We are also looking at commercial tools and solutions. And just one slide quickly about what government agencies and solutions are asking. Here, the Land Transport Authority is saying that autonomous vehicles are going to be inevitable. How do I make sure these autonomous vehicles are going to be safe on the ground? At the same time, they are going to be cyber secure. They're not going to be remotely taken over by someone at will and turn that into a weapon. So these are very real concerns of transport authorities, agencies who are trying to ensure some form of conformance and standards. So this is a question, and obviously we are trying to define this as a problem of how to systematically identify the attack surfaces. How do you then come up with the strategies based on past knowledge base on the most probable attack scenarios that we should be subjecting for penetration testing. And then obviously the third question is how to do it as fast as we can, because we don't want the vehicle to be there waiting forever. So there are research questions in all three aspects, and it's a very interesting problem for us. We are also collaborating with an industry partner, British Aerospace Engineering, and they are interested in, from a commercial solutions perspective, all different topics, but currently we are looking at how to advance their cyber threat intelligence, and also looking at some of the behavioral analytics work. So this is just started with about $3 million of funding. And insurance company, AIA, and the like, are also approaching us, and they got lots of problems in there in trying to bring about something like a cyber range and a SOC for themselves. So they're happy to share data, they're coming together, and we think it's going to be very interesting opportunities to be able to serve the industries, the agencies at the same time as to develop technologies. That's as far as I will go about the brief introduction. And these are the areas, though, because as you can see, cybersecurity is such a huge space. I started embedded systems about maybe 20 years ago, and I felt embedded systems were too huge. Anybody and everybody, even people working in formal verification, can indeed be saying that, oh, I work on embedded systems too. So cybersecurity is such an area. But we are narrowing it down to all these 4 bullet points, if you like, or major ones. Security and trustworthiness of embedded systems we're very interested in. We have competencies. Cyber threat detection and attack attribution is another, where we have colleagues working, and I will be talking about my semantic-based security analysis in this context. Cyber and cyber-enabled crime and forensics, because our government agencies are also approaching us for solutions for law enforcement and increasing the awareness of public and so on. There are a number of issues and challenges there. And also holistic approach to cybersecurity. People are even questioning about social foundation of cybersecurity, trends, issues, and challenges in terms of international laws and policies. So we are fortunate. We are able to position ourselves as an interdisciplinary research group, and that much more one can do, but these are the areas. So let me just quickly go into this semantic-based security analysis. There are 3 areas. This is work done with my colleagues, and the first, of course, is a simple question of, can we remove vulnerabilities that exist in a functionally correct code? Can we remove them? Can we remove the holes based on the past vulnerabilities that have been detected? So can we systematically do that? And ideally, can we do that at the binary level? So this is one question we are asking. And the second question is that then how do we remove malware? Yes, but how do we do it in a more smart way so that you can identify 0 days as well? And that's the second thing. So these are offline operations. So how to make sure your software is more hardened. And the second one indeed is to how to remove malware so that they're kind of being attack resistant to compromisation free maybe as a proposition. And the third one indeed is to turn around and say, in spite of all these things, there could be compromises. How do you develop some runtime methods in order to be able to monitor at runtime for anomalies? And so this is a 3-pronged approach in the semantic-based security analysis we are working on. And the case is made. The method we are developing, hope it doesn't get into the wrong hands, because if it does, they can use the vulnerability, detect the vulnerabilities faster and end up causing even more headaches much sooner than we would like them to. So case is made that there is a vulnerability detection is going to be, is gaining a lot of popularity, and there are pockets of activities, but current approach is predominantly manual. So how do we do this? How do we automate this? So we have come up with a method. It's a work in progress. There are 3 main areas I mentioned. One is the semantic patch analysis. Identify potential regions in your complex code. so the patches. So we call them as semantic patch analysis. And the other one, of course, is the vulnerability extrapolation. So once you identify them, you're trying to go through a process called vulnerability extrapolation, and I have a slide that follows soon just to explain that. And then after that, you do target-based smart fuzzing. So you do the fuzzing in a very targeted manner so that you can use the available time more wisely and the resources more wisely. So this is a three-pronged approach that we have established over the past 3-4 years of work. And then if you look at the vulnerability extrapolation, you can see we have a signature program that based on our past knowledge base. Here's a target program, do the disassembly, we have an intermediate representation, and we do some pre-filtering process, and then we come up with the filtered functions are being located, and then you can see it goes through this particular process for semantics-based signature matching, and that in turn will determine the extrapolation process. So fairly complex, but it's a lot of machine learning involved here, and also deep program analysis. So we are combining the two to be able to try and do this extrapolation process. And with the state we are in, we managed to put that to applications. So here the beauty is that we can take the exe files, we don't need the source code, and we have a way of doing this vulnerability detection process, and we have identified a couple and more from the MXL2. And now the question now is, they got some money, that research team managed to win some prize awards from Adobe and others. I think the current count is about 35,000 US, and so therefore working overtime, hoping that they can find more bug bounties and so on. So it's showing potential, and so we are quite interested in this. And when we presented this to an MNC, and we've now been tasked to take their third-party solutions, which apparently have passed their pen test process, penetration testing. That takes apparently up to about 6 weeks, which is too long for them, but you have to go through in order to conform to certain standards. So we are going to be having access to the ones that have passed the test, and we're going to put them through this vulnerability detection process. So it's about to happen, and it'll be very interesting for us as to how good or otherwise and issues here. I must mention, though, that in this particular 3 areas, there's quite a lot of work to be done. Smart fuzzing has to become smarter. Vulnerability exploration must also be very smart, because what you're doing is you're being very selective and in trying to do the fuzzing in a very targeted manner. So, because otherwise you're going to be there forever. So this is the thinking. Okay, so we also took one of these popular drones and the software, and we also found a number of vulnerabilities in it. So that's giving us the potential that there is something here. And the potential areas we are thinking of indeed is that security certification of software. We think eventually that we could move into that directions, and also trying to look at emerging technologies and applications where we can apply this. So that is the first of the 3-prong approach, vulnerability detection. And the second one is in the JavaScript-based malware detection. And over here, this is for the JavaScript, so JavaScript detection and classification, we call it. And we have a clever approach of combining both static and dynamic confirmation. So it's a hybrid approach, and we come up with a method based on for the matching, and some machine learning based for classification, and from there we look at dynamic confirmation just to ensure that its behavioral features are indeed confirming the malware, presence of a malware. It can be even the 0-day malware. Okay, so we do that, and then if it fails, of course, then we have a step for manual validation. So we do this, and we kind of compared with the different benchmarks. We are getting better results. I don't want to go into the details. We also did something. We crawled, about 1.4 million widely crawled scripts, And then what we did was, we applied our method. We found about 1,500 or so snippets. And then what we did was we randomly selected about 100 cases and then looked at them just in detail to see 99 true positive cases and 1 false positive, which I think is pretty good. Okay? So what we then did was to take this 99 and subject it to all the other commercial tools and see how they would perform. Okay? And in here you can see 11 of the 99 true positive cases are missed by all the tools. Okay? So this is fairly encouraging for the research team because this hybrid approach of both static and dynamic analysis is yielding much better results. Okay? So this is a work that is ongoing. I'll quickly touch on the 1 minute. Okay. All right. So I can quickly, I forgot. I thought they were taking a photo using an iPad, but now I see that there was an A4 sheet. Okay. It's my eyesight, and maybe I'm choosing to ignore all that. So, okay. So, okay, quickly, we've done that for also Android malware detection. And again, you can see we do some machine learning and classification process. And I wouldn't go into the details. We are credible in terms of our accuracies and performance. And we also do something like machine learning-based kind of detection and also a classification process. So we can classify the type of malware. I think that's important. Not just the malware, but what kind of malware it is. And that possibly helps maybe to inch towards some form of attribution capabilities. So this is somewhat good, I think. And so you can see that we had detected 45 and all the others are much, much lower in performance. The last one, just a quick mention here in this slide alone, I wouldn't go into it. This is a very interesting project with about 20 research team working. I'm the lead PI. And we started off by questioning the entire stack of computer architecture from the processor core to kernel and to libraries and also to application. And there is a group working on compositional verification to make it as verified as possible. But we are more interested in runtime verification on this side. So what we are trying to do is we are trying to monitor operations at the hardware level by monitoring the performance counters and trace event buffers. From here, we are trying to see any anomalies. Remember, we have a knowledge base from the malware analysis background, right? So we have behavioral features. And we are trying to translate that over here, whether we can monitor this at runtime. And also at the operating system, what else can we watch at the operating system, the behaviors, and also at the application layer. So you can see this 3 hierarchy, and then vertically looking down, can there be a combined approach of somebody looking at a short distance, maybe at a medium distance, and also much far apart. So we are beginning to develop a technologies that could possibly monitor the entire operation at runtime. So this is the mission of this particular program, and in the interest of time, we got some demonstrators in place to be able to probe this very nicely, some behavioral signatures, and I'll stop. Thank you.